Good afternoon, class. We are looking at Chapter 4, Application of Derivatives, Section 4.1, Maximum and Minimum Values. Chapter 4, Application of Derivatives. The sections we're going to cover: 4.1, Maximum and Minimum Values; 4.2, How Derivatives Affect the Shape of a Graph; 4.4, Optimization Problems; 4.6, Anti-Derivatives. Especially for the sake of last section, 4.6, anti-derivatives or integration, we need to be very comfortable with differentiation formulas so we can go with the reverse process. Various formulas are given to you here. Delta y is precisely f of x plus delta x minus f of x. That means if you have a curve, the rise along the curve, this distance is delta y. dy, the rise along the tangent line, AB, is dy, and it's f prime of x times dx. Delta y can be approximated by dy as long as delta y can be approximated by dy as long as delta x is pretty small. If we call this pair a comma f of a, we can use the point slope y minus y1 equals m times x minus x of 1 to find the tangent line known as linearization. So do I have to memorize the formula for L of x? No, it's ultimately the point slope that we have learned. 4.1, maximum and minimum values. Definition: critical point, or short CP. A critical number or point of a function f is a number c such that f prime of x equals 0 or f prime of x dne does not exist. Here's an example. Example 1, find the critical numbers of f of x equals x cubed plus 3x squared minus 24x. Here's the process. To do so, number 1, we want to find f prime of x. So x cubed, 3x squared. 3x squared, the derivative is 6x. Minus 24x, the derivative is negative 24. Therefore, f prime of x is 3x squared plus 6x minus 24. Step 2, f prime equals 0. We want to set this equal to 0 and solve. To do so, I'm going to factor out number 3, and it becomes 3 times x squared plus 2x minus 8 equals 0. I'm going to factor x squared plus 2x minus 8. I want two numbers. The product is a c, or negative 8. The sum is b, or 2. So the answers are positive 4 and negative 2. The first one gives us x equals minus 4, and the second one gives us x equals 2. So that was the second step. As far as the third one is concerned, you also have to look for where f prime is undefined or dne does not exist. F prime itself is a polynomial. It's a polynomial of degree 2, or a quadratic function. It exists everywhere, and therefore f prime of x dne does not produce any solutions, and we are done. Formal definitions: maximum or minimum points on a curve. Local, also known as relative extreme values. Extrema is the plural of the Latin extremum. A local minimum is the minimum value within some open interval. Local minimum occurs at a point C in an open interval of A to B in the domain if f of c is less than or equal to f of x for all x values in the open interval. So local mean in some open interval, this has the smallest y coordinate. A local maximum is the maximum value within some open interval. Local maximum occurs at a point C in an open interval A to B in the domain if f of c is larger than or equal to f of x for all x values in the open interval. So we have local max. In short, these two refer to peaks and valleys. Local max, local max, local mean in some open interval. Absolute, also known as global extreme values or extrema, are either maximum or minimum point on a curve in the entire domain now. So absolute minimum occurs at the point C if f of c is less than or equal to f of x for all x values in the domain, as it's the case here. So this is an absolute minimum. No other point has a smaller y coordinate. No other point is below that point. Absolute maximum occurs at the point C if f of c is greater than or equal to f of x for all x values in the domain. This point is the location of an absolute maximum because no other point in the entire domain is above that, having a larger y coordinate. So in short, what are we discussing here? Local mean, local max, local mean, local max, peaks and valleys. Peaks are max, valleys are mean. Local mean, local max, local mean. This one is also an absolute mean. Local max, local mean, local max. This one is also an absolute max because no other point is above that, having a larger y coordinate. Local or relative extreme values. Fermat's theorem. If a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime of C must be 0. As we look at this example, notice over here we have a smooth curve, and this is a local max, smooth curve, local mean. Because f prime exists, this short tangent line is horizontal with the slope 0. So f prime is 0 here, f prime is 0 here, as it's indicated here. On the other hand, over here, which is a local maximum, and it is also an absolute maximum because no other point has a larger y coordinate. In this case, as you can see, we have a sharp corner. F prime does not exist. So if f prime exists, must be 0. Note, local extremes in the interior of the function occur where f prime is 0 or f prime is undefined. So if we have local extrema, either f prime is 0 or doesn't exist. Maxima and minima of a function always occur at critical points. So if we have maximum and minimum, those points must be also critical points. But critical points are not always maximum or minimum values. Not the other way around. The converse may not be true. We have to further investigate. So again, in short, if we are sure we have local extrema, it's either f prime 0 or f prime doesn't exist. But if we have a critical point, it may be a local max, local mean, or may not be. Let's further investigate this. Extreme values can be in the interior or the end points of a function. End points can never be a local extremum. They can only be absolute, if that. So let's look at this simple example everybody is familiar with. Y equals x squared is a parabola with the domain of negative to positive infinity, which is an open interval. Here's 0, 0. The absolute minimum occurs at this point, which happened to be a local minimum as well. This continues indefinitely. There is no absolute max. There is no local max. As far as the writing is concerned, for this one, this is equal to the y coordinate. So one might write this is equal to 0 at, then you can write the pair, or x equals 0. Depends on how they want to write it. Sometimes they want the pair, sometimes they just want x, sometimes they just want the value of the absolute or local minimum maximum, which is the y coordinate of the function. Let's look at the same function, but we are going to change the domain to a closed interval of 0 to 2. So this is a closed interval. And this point obviously has the same coordinates 0, 0 as previous page. This one has coordinates 2, 4. This one is the absolute minimum. This one is the absolute maximum. And because those are end points, they are not considered local. So we don't have any local extremum. So as far as the writing is concerned, this would be just like before. This would be like 4 at this point. So again, end points cannot be local extrema. They are not. Let's make a slight change. And now the same function, the domain will be half open, half closed, meaning 0 is not included, but 2 is included. That's why we get a hole here. And therefore, there is no minimum. But the same thing, 2, 4 remains as absolute max. Just as the previous page, this is equal to 4 at this pair. However, there are no local extrema. We don't have a local max. We don't have a local mean. Now, if we make this an open interval, none of the endpoints are included. So we get a hole here as well as here. We don't have a minimum. We don't have a maximum. We don't have any local extrema either. So now we are ready to look at extreme value, also known as closed interval theorem. If f is continuous over a closed interval, a to b, then f has a maximum and minimum value over that interval. So two things must be continuous and the interval must be closed. The endpoints must be included. In a case like this, absolute max, which is a local max also, absolute mean, which is a local mean also, maximum and minimum at interior points of the graph, somewhere between A and B. absolute max, absolute mean, max and mean at endpoints, but we don't have local extreme. So it's a closed interval. So it happens to be at the endpoints. Absolute max, which happen to be a local max also, absolute mean. Therefore, maximum at interior point, minimum at endpoint. To find absolute max and mean values by extreme value known as closed interval theorem, number one, find the critical points, CPs, and evaluate the function at those points. Original function, f of CPs. Number two, find the values of the function at the endpoints, f of A as well as f of B. So, number one, evaluate the function at the critical points. Number two, evaluate them at the endpoints. Finally, third step, largest value is the absolute max and smallest value is the absolute minimum of the function. So pretty straightforward, everybody. Here's a simple example. Example to find the absolute max and minimum values of f on the given interval, where f of x is given as 1/3 x cubed minus 9x, and the closed interval of minus 6 to 0. Before we start, we have to justify the usage of this extreme value or closed interval theorem. So we have to justify whether the function is continuous or not, and what is the domain. This is a polynomial of degree 3. The domain is all real numbers. So its domain is all real numbers, or it's continuous from negative to positive infinity. Therefore, it makes it continuous in the given interval of minus 6 to 0. So extreme value or closed interval theorem. F is a polynomial of degree 3. It is continuous from negative to positive infinity. And therefore, it's continuous in the given interval of negative 6 to 0. So we can move on with the methodology. Number one, find CPs by first finding f prime of x. Now, what is f prime of x? 1/3 times 3 makes it 1, x squared minus 9. So f prime of x is x squared minus 9. So we found f prime. Now, set it equal to 0 and solve. Two ways to do that. You can say x squared equals 9 and solve it, or factor it into x plus 3x minus 3. This gives you negative 3. This gives you positive 3. So we got two answers for this part. So we found f prime. We set it equal to 0. It has two answers. Or does not exist. We have to check that part also. F prime does not exist. That means x squared minus 9 does not exist. This is a polynomial of degree 2 or quadratic function. It exists everywhere. So it produces no solutions. This means no solutions. This is a Greek letter phi. It's not 0. And it means no solutions. Then what happens? There are only two answers. We look at the given interval. Is negative 3 in between negative 6 and 0? Yes. Is positive 3 in between? No. So you can't use this one. It's not in between. You can only use this one. So we write down Negative 3 is an element of this set. This is it. This is in set theory. We use this one and this one in set theory, and it's red. An element of, that's how you read it, an element of. And so we are going to go to the next step. Find f of a, f of b, and the critical point. So you plug in -6 in here, 0 in here, and -3. So you want to evaluate those, which means, for example, 0 class is very simple. Everything goes to 0. So that takes a split second. If I go with -6, that means I put 1/3 of -6 cubed minus 9 times -6. So 1/3 of that minus 72 plus 54, and that's -18. If I go with -3, one-third of -3 cubed minus 9 times -3 makes it 9 negative minus 27 plus 27. So it's 18. So we have -18, 18, and 0. Now, third step, absolute max, the largest, absolute mean is the smallest. Here's the largest one, absolute max is the smallest one, absolute mean. Absolute max is 18 at this pair, absolute mean is this at this pair. So the way I write that, absolute max equals 18 at -318. Absolute mean is -18 at -6, -18. They may want the pair, they may want the x coordinate only. You want to pay attention to how they want you to answer the question. Example 3, find the absolute max and mean values of f on the given interval. F of x is x plus 3 to the power of 2/3 minus 5, the interval of -4 to 5. So the first thing is, can I use the extreme value or closed interval theorem? So two things must be done. Number one, it must be a closed interval which is given, but is this a continuous function in the interval of interest, in this interval? So first notice, we can rewrite this as f of x is the cube root of x plus 3 squared minus 5. So it's a cube root, meaning think about cube root of x, then it's been shifted to the left by 3 units. When you square it, the positive side gets larger, the negative side the negative side, which is below the x-axis, flips over, becomes positive, and then we are bringing it down by 5, as far as graphing is concerned. And as you know, a cube root, a basic cube root, looks like this. The domain is all real numbers. Again, you shift this to the left by 3, and the positive part gets larger, the negative part flips over, and then you bring it down by 5. So the domain is all real numbers. So to use the extreme value theorem, f, meaning this function, is a cube root function. It's continuous from negative to positive infinity. Therefore, it's continuous in the given interval of -4 to 5. We are going to differentiate this. The first step is finding f prime of x. 2/3 x plus 3 to the power of 2/3 minus 1 or negative 1/3 times the derivative of the inside, which is 1 and negative 5. It's just a constant. So differentiation shouldn't be a big deal. And we rewrite this by putting this underneath and making it to the power of positive 1/3. So we found f prime of x as 2/3 x plus 3 to the power 1/3. Now, as you notice, f prime is in a fractional format. We want to know where f prime is 0, where f prime doesn't exist. So I'm going to remind you, if you have a fraction of a to b equals 0 if a is 0, when the numerator is 0. That's all. A to b is undefined when b, the denominator, is 0. When we go back to this, the numerator is a number, whether it's positive, negative, large, or small, makes no difference. F prime equals 0 doesn't give us any solutions. Remember, this is phi. Now, f prime is undefined or does not exist. You set the denominator equal to 0 according to this. So when you set this one equal to 0, clearly when you choose x equals negative 3, the denominator becomes 0. And you're going to ask yourself, is negative 3 in between the given numbers for the interval? And the answer is yes. Therefore, the function must be evaluated. We're going to go to the second step at these two endpoints as well as this critical point. So that's what number 2 says. So evaluate the function at the endpoints negative 4, positive 5, and of course, this negative 3. That's what we are going to look at, everybody. That's a pretty simple process, everybody. We are going to go back to the original function. And by the way, negative 3, if you plug in, and it's easier to go with this one. The second, negative 3, if you plug in, this goes to 0. So the answer is minus 5. Please understand this. This is simply minus 5. If I plug in minus 4 here, minus 4 and 3 is negative 1. And cube root of that is negative 1. So I have negative 1 squared, right? Minus 5, which makes it 1 minus 5 or negative 4. If I plug in 5, 5 and 3 is 8. Cube root of it is 2. So I get 2 squared minus 5, which is 4 minus 5, negative 1. So we get these values. I'm assuming nobody has any problem with those evaluation basic math. So since all of them are negative, this is the largest value. So absolute max at this pair. This is the smallest value. Absolute mean equals negative 5 at this pair. So we can write absolute maximum equals negative 1 at 5 comma negative 1. Absolute minimum equals negative 5 at negative 3 comma negative 5.